we start lesson 5, which is on continuity. So in the last two classes, we looked at limits of functions, and a continuous function is just a function which has a nice graph. It doesn't jump around. So if you have a graph that looks like that, that kind of thing is continuous. But something which jumps, and we have like these jumps or gaps in the function. When something like this happens, the function is not continuous or discontinuous. A function that you can draw smoothly without taking your pencil off the paper is a continuous function. So this is the intuitive definition of what continuity of a function means. In calculus, we study mostly, almost exclusively, continuous functions. So there's a formal definition of continuity, and it is the following. So a function f of x is continuous at a point C if the following three conditions are satisfied. First of all, f of c is defined. So the function has meaning at the point C. Second, when you take the limit of f of x as x approaches c, this limit exists. And third, the limit of f of x as x approaches c is exactly equal to the value of the function at c. So an example of a function that's not continuous at a point. Suppose we let f of x be defined as follows, that it's equal to 1 when x is not equal to 3, and it's equal to 2 when x does equal 3. So the graph of the function looks like this. When x is equal to when x is equal to 3, the value of the function is 2. Should draw it properly. So when x is equal to 3, the value of the function is 2. But for all x different from 3, the value of the function is 1. So this function is this horizontal line. At the point 3, it jumps up 1, and then it continues at 1 forever after. So this function is defined, and so this function is not continuous at x equals 3. Why not? Well, f of 3 is defined. F of 3 is equal to 2. And the limit exists. So f of 3 is defined. F of 3, in fact, is 2. The limit as x approaches 3 of this function f of x exists. It's equal to 1. Let me just say exists. Because as you approach 3, the function is just moving along this horizontal line and it approaches 1. But the limit of f of x as x approaches 3 is not the same as the value of the function at 3. The value of the function at 3 is 2. The limit is 1. So this is an example of what it means for a function to be continuous or not continuous. And there are lots of very good pictures of this in the textbook. And we say that a function f of x is continuous on an open interval I, let me just write it, AB, if f of x is continuous at every point in the interval. So here's some examples. Suppose we look at f of x equal 1 over x. So the graph looks like that. This function is not defined at x equals 0. You can't divide by 0. So the function is certainly not continuous at x equals 0. But it is, because it can't be continuous where it's not even defined. But this function f of x is continuous for all x different from 0. So it's mean this is continuous on the open intervals from 0 to infinity and from minus infinity to 0. So at any point along this hyperbola, the function is continuous, but it's not continuous at 0, it's not defined at 0, and in fact, the limit as you approach 0 doesn't even exist. Okay. Let's look at another example. Suppose we take the function g of x equal to x squared minus or over x minus 1. So this is not defined at x equal 1, which you can't divide by 0. On the other hand, you can say the following: g of x for x different from 1, you can factor x squared minus 1. It's x minus 1, x plus 1. And these terms cancel. So g of x is in fact equal to x plus 1 for x not equal to 1. So the graph of this function looks like this. It's just the straight line, y equals x plus 1, only it's not defined when x equals 1. So this can't be continuous at x equal 1 because the function is not defined there. But it is true nonetheless that the limit of g of x as x approaches 1 exists, and it's equal to 2. As you approach 1, the function approaches 2. Any questions about this? So continuity is a concept that you have to think about a little bit, or maybe think about a lot to get a good understanding of. Here's another example. H of x is defined as follows. It's x plus 1 for x less than or equal to 0, and e to the x when x is greater than 0. What does this function look like? Well, when x is less than or equal to 0, this is a line with slope 1 and y-intercept 1, a straight line. And for x greater than 0, this is e to the x. Now, h of 1, sorry, h of 0 is 1. The limit of the function h of x as x approaches 0. Whether you come from the left or from the right, this exists. And the limit of h of x as x approaches 0 is 1, which is the value of the function is 0. So even though this function has a somewhat complicated description, straight line followed by exponential, h of x is continuous at x equals 0. And in fact, h of x is continuous everywhere on the interval from minus infinity to plus infinity. Here is just this continuous straight line. Here is the exponential. And again, if you use the pencil and paper test, I can draw this curve without taking my pencil off the paper. So that's a measure of how continuous it is. If we take the function y equals sine x, that's just your ordinary sine wave. This is continuous everywhere. From minus infinity to plus infinity. Now, I defined continuity on an open interval. Suppose we want to think about closed intervals. So the closed interval AB, this is the set of all x where x is greater than or equal to A and less than or equal to B. So you include the endpoints. Remember, the open interval is the set of all x such that x is strictly between A and B. So the endpoints of the interval are not contained in the open interval. They are contained in the closed interval. And if you want to talk about continuity on a closed interval, so you have to have the notion of what's called a one-sided limit. Remember, for the ordinary notion of continuity, if you have a number c, you take the limit as x approaches c from the right side and from the left side, from both sides. In a one-sided limit, you would take the limit that say as just as x approaches c from the right, not from the left, or the other way around, just from the left and not the right. So just to sort of draw a picture of what this could be, suppose we have the following function. So suppose we have a function f of x, which is equal to 1 for, this is some number c. Say x less than or equal to c, and it's equal to 2 for x greater than c. Now, as you approach this number c, there's no limit, because it matters whether you're coming from the right or from the left. But we do have the one-sided limits. If we take the limit as x approaches c, and I'll put a minus sign, which means coming from the negative direction from the left, this function is 1, 1, 1, 1, 1, and the limit is 1. If you take the limit as x approaches c, I'll put a plus sign from the plus side. It's 2, 2, 2, 2, 2, and so on. The limit of this function is 2. So this is an example of a function that has a limit from the right and has a limit from the left. That is, it has the two side. It has the one-sided limits, even though it doesn't have an ordinary limit. Here's another nice example. Suppose we have the function f of x equals the square root of 4 minus x squared. Now, where is this function defined? The domain of f of x, that is where this function can be computed. You're taking a square root, so what's under the square root has to be greater than or equal to 0. So this is the set of all x such that 4 minus x squared is greater than or equal to 0. 4 minus x squared greater than or equal to 0 is the same as x squared is less than or equal to 4. And if you think about it, that means x can't be any bigger than 2. It can be negative, but it can't be less than negative 2. So the domain of this function is the closed interval from -2 to 2. And the graph for this function, if you have y equal the square root of 4 minus x squared, if you square both sides, you get y squared equals 4 minus x squared, or x squared plus y squared equals 4. So this you should recognize is the equation of a circle. And I'm taking just y non-negative, it's a square root. So this is the graph of this function. It's a semicircle. And the limit of f of x as x approaches 2 from the left, put a minus sign there, as x approaches 2 from the left, the function is going to 0. The limit of f of x as x approaches 2 from the right does not exist because the function is not even defined there. Okay. So again, in calculus, there are a lot of concepts that you're probably unfamiliar with, which is good. That's why you're here, to learn something you're not familiar with. And so we say f of x is continuous on a closed interval. From a to b. If first, f of x is continuous on the interior, the open interval, all in there is continuous, and the limit of f of x as you approach b from below exists and is equal to f of b. And the limit of f of x as you approach a from the right exists and equals f of a. So this really is the natural definition of continuity on a closed interval.
Professor.
Yeah.
Quick question. So the minus and the pluses, what are those for?
I mean, here and here.
Yes.
So when you're looking at a one-sided limit, to say the limit of, this is the limit as x goes to b minus, you're looking at x that approaches b from the left, from the negative side, not from the right. So this means take the limit of this function as x approaches b from the left. The plus side means you take a limit only on the side of numbers that are bigger than a, the plus side. So in the example I showed earlier, we have a function And this is its graph. There's some number c, and for x less than c, the value of the function is 1. For x strictly bigger than c, the value of the function is 2. Now, as x approaches c, this function doesn't have a limit. There's nothing that the function gets closer and closer to as you approach c. But if you only look at the one-sided limits, like here, the limit of this function as x approaches c minus, that means from the left. As you approach from the left, this is the constant function 1, and the limit is 1. Here you have a plus. As you approach this number from the right, the plus side, the function is constantly equal to 2, and the limit is 2. So that's what the plus and minus signs mean.
All right, thank you, Professor.
Yeah. Any other questions? So there's some basic properties of continuity that I will write down. And they're sort of the things you would expect, that if you take the sum or difference or quotient of continuous functions, they stay continuous. So the theorem 211 in the text says the following. So B is some real number, and F and G are functions which are continuous at the point C. So then the following functions are also continuous. Scalar multiples. The function b times f of x. Just take a continuous function, multiply it by a number, it's still continuous. Sum and difference. F plus g and f minus g. The product of continuous functions. And the quotient. F divided by g, so long as you're not dividing by 0, g of c is not 0. And the other very important characteristic of a continuous function is that if you compose two continuous functions, the new function you get also is continuous. So if g is a continuous function, at x equals c, and f is continuous at g of c, then f composed with g of x, that's f of g of x, is also continuous at c. So functions like What? Well, the function 3x is continuous, and the trig functions are continuous. So the sine of 3 of x is continuous. X squared plus 1 is a continuous function, and it's always positive. Compose that with the square root, and that's continuous. 1 over x is continuous when x is not 0. And the tangent of 1 over x is continuous wherever this is defined. So first of all, 1 over x is not 0, and the tangent is sine over cosine. Cosine of 1 over x is not 0, which means 1 over x is not a multiple of pi plus a half, which means x is not 1 over a multiple of pi plus a half pi. So here's a kind of exercise that uses just the definition of continuity. It's a problem. Find the intervals where the function is continuous. So the first example to investigate is tangent of x. Where is this continuous? This is sine x over cosine x. Now, sine x is continuous everywhere. Cosine x is continuous everywhere. So this function is continuous wherever the denominator is not 0. And the denominator is not 0 at whenever x is not pi over 2 plus any multiple of pi. So this is 0, pi, 2 pi minus pi. This is pi over 2, 3 pi over 2 minus pi over 2. This function is continuous on these open intervals. But not at the endpoints. So with pi over 2 plus any multiple of pi, this function is undefined and not continuous. But everywhere else, it is continuous. Here's another example. G of x is the function which is defined to be 0 when x is equal to 0. And when x is not 0, it's the sine of 1 over x. Now, this is defined everywhere because sine is defined everywhere for every number. 1 over x is, when x is different from 0, 1 over x is well defined, just a number. This makes sense and this makes sense. So this is certainly continuous whenever x is greater than 0 or less than 0. But what about continuity at x equals 0? Well, the limit of g of x as x goes to 0 just the limit sine of 1 over x as x goes to 0 does not exist. If we were to graph this function, the sign is always between +1 and -1, and this function would be oscillating, but faster and faster and faster. And it doesn't approach any limit as x goes to 0. So you ask, is this function continuous at x equals 0? No. But everywhere else, all positive real numbers, all negative real numbers, the function is 0. If we modify this example a little bit, we do get a continuous function everywhere. And the modification is the following. Suppose we let h of x be equal to 0 at x equals 0. For x different from 0, x times the sine of 1 over x. Now, if you look at the line y equals x, it's that straight line. And if you look at the line y equals minus x, it's this straight line. And this function, x sine 1 over x, when sine 1 over x is 1, this function is equal to x. When sine 1 over x is -1, this is equal to -1. And what the graph of this function is actually this dampened sine wave. It's oscillating inside these two straight lines. And for this function, the limit of h of x as x approaches 0 is equal to 0. And so this function h of x is continuous. For x away from 0, this is just a composite function of continuous functions. This is continuous for all x from -infinity to +infinity, including 0. So this is a lot to digest, and say think about it for a minute, and I will check the attendance today as you are thinking about it. So let's see who's here. Alex Amin, Manon, Negron, Leonardo, Lopez, Atkins, Bello, Gordon, Fletcher, Rizzoli, Lorenzo, Reyes, Frias, Rob Narain, Beltran, Segura, Molinuevo, Vega, Garcia Vega, Fahim, Conwell, Alcantara, Wiley Wandago,
I'm here, Professor.
and one mysterious person named Galaxy S10. What is your last name?
Isaiah Tillett.
Sorry, how do you spell your last name?
Tillett, T-I.
Yeah, okay, gotcha.
Mhm.
So you're logged on as Galaxy S10?
Yeah, I'm trying to figure out
Yeah,
how to
no
switch
problem,
that.
whatever. That's fine. Anyone whose name I didn't call? No, okay, good. So there is one extremely important theorem about continuous functions that's called the intermediate value theorem. And again, in Math 175, the minimum or the maximum or what you're really required to learn is how to solve actual calculus problems. But it's important to know at least a little bit about the theory behind them. They're never going to ask you to prove a theorem on an exam or even state a theorem. So you might need to know the statements of some theorems in order to solve some problems. But the big theorem in this section on continuity is something called the intermediate value theorem. Which says something like you can't get from A to B without going through C. So the statement is as follows. We have a function f of x, which is continuous on the closed interval from A to B. And f of A in this case is different from f of B. And let k be any number between f of A and f of B. Then there is at least one number c such that c is between A and B, and f of c is equal to k. Let me give a simple example of what that means. Suppose we have a function from A to B, and let's say at A it's negative, and at B it's positive. This is the x-axis, which is the line y equals 0. And the continuous function it has this value at A and this value at B. And the statement is there's some point C where the function is 0. That is, you can't get from here to here if the function is continuous without actually crossing the line. You can't jump. I mean, that's not a continuous function. If you're going to get from here to here, whatever you do, it'll be really complicated. But at some point, you have to cross the line. That's exactly what the intermediate value theorem says. Not just for hitting the value 0, but in the general case, we have f of x on the interval from A to B. So This is the point A comma f of A. And this is the point B comma f of B. And we take a number K between f of A and f of B. So this is the line y equals K. And the intermediate value theorem says if you, as you go from this point to this point, you have to cross the line. So there's some point C, and at that point, sorry, this is line y equals K, f of C is equal to K. Right? I mean, if you're going from here to here, you might cross the line at a lot of points. The intermediate value theorem says there's always at least one. That's the intermediate value theorem. There's no way, if you're continuous, that you can jump across the line. All right, well, let me
Quick
do
question.
some exercises just to try and make clear what's going on.
Professor,
Yeah,
what does the graph on the right show?
this?
Yeah.
Uh,
That's what you're not supposed to do, or that's also valid?
this is A f of A. This is B f of B. The intermediate value theorem says your graph can't get from here to here without crossing the line. Maybe it crosses just once. It could cross 20 times. That's all.
Okay.
It has to cross the line at least once. But there's nothing that says it can't cross the line twice.
All right, thank you.
Like if you had the function y equals sine x, which is continuous, let me make it y equals cosine x, which is continuous on the interval from 0 to 4 pi. Now, sorry, make it 0 to 5 pi. So the cosine of 0 is 1. The cosine of 5 pi is -1. Suppose I pick a number like a half, which is between 1 and -1. So what does the graph of the cosine look like?
We can't see what you're doing.
I'm just drawing the cosine. Right? That's the cosine. And here is the line y equals a half. Cosine of 0 is 1. Cosine of 5 pi is -1. A half's a number in between -1 and +1. The intermediate value theorem says the cosine's equal to half for some number between 0 and 5 pi. In fact, if you look at this graph, you see it's equal to a half at 1, 2, 3, 4, 5 different points. Well, that's fine. That's okay. 5 is at least 1. So all this is saying is that the intermediate value theorem guarantees at least one point exists with a certain property, but there could be more than one. That's not excluded. So some of the homework problems are to find out if certain limits exist. So we have determine if this exists, the limit is x goes to 5 plus x minus 5 over x squared minus 25. So that means we want to look at this expression and take the limit as x approaches 5 from the right, x bigger than 5. That's what the plus sign means. So of course, x squared minus 25 factors. These cancel. So this is the same as x1 over x plus 5 as x approaches 5 from the right. And this is 1/10. That's the limit. What about the limit of the absolute value of x divided by x as x goes to 0 from the left, minus sign? Now, remember the absolute value of x is equal to x if x is greater than or equal to 0, and minus x if x is negative. So if x is greater than 0, absolute value of x over x is 1. If x is less than 0, absolute value of x over x is minus 1. As you approach 0 from the left, that means through negative numbers, this limit is minus 1. In fact, for this function, if you look at this, this says the graph is equal to 1 for x positive, and it's equal to minus 1 for x negative. So as you approach 0 from the left, the limit is minus 1. If we were to approach 0 from the right, the limit would be plus 1. Here we have the following problem. Compute the limit as x approaches 3 from the left of the function f of x, where f of x has this definition. It's equal to x plus 2 over 2 if x is less than or equal to 3, and 12 minus 2x over 3 if x is bigger than 3. So what does the graph of this function look like? If x is less than or equal to 3, y is x plus 2 over 2, which is x over 2 plus 1. And if x is greater than 3, y is 12 minus 2x over 3, which is 4 minus 2/3 x. So what does this graph look like? So when x is less than or equal to 3, this is the straight line, 1 plus x over 2. When x is equal to 3, this is equal to 5/2. When x is equal to 0, it's 1. So for x less than or equal to 3, it's this straight line. When x is bigger than 3, it's the line 4 minus 2/3 x. When x equals 3, that's equal to 2. And that's just a line that goes down like that. So this function, it's kind of a V-shaped function. It goes up, and here it turns around. At x equals 3, where the expression for the function changes, the value of the function, oops, I think I miscalculated something. When x is equal to 3, 3/2 plus 1 is 2.5. Let me draw this better. So f of 3 is 3/2 plus 1 is 5/2. This function is different. It's 2, and then it goes down. So in fact, this function does have a jump as you approach 3 from the left or the right. As you approach 3 from the left, it's this. As you approach 3 from the right, it's this. And the limit for this function as x approaches 3 from the left is 5/2. The limit of this function as x approaches 3 from the right is 2. And these are different. So this function has right and left-sided limits, but they're different. This is number 35. Not one of the homework problems, but these are good problems. We have the function g of x equal to square root of 49 minus x squared. This is only defined where 49 minus x squared is greater than or equal to 0. That means x squared is less than 49. That means x is between -7 and +7. So the domain of the function is this closed interval. And this function is continuous on the whole closed interval. The limit of g of x as x approaches 7 from the left, the graph of this function looks like that, is 0, and the limit of this function as x approaches -7, but from the right, is also equal to 0. So this function is continuous on the open interval, has two-sided limits there, and it has one-sided limits at the endpoints of the interval. Now, there's one other important concept connected to continuity that I want to mention. And it's the concept of a removable discontinuity. So a function f of x has a removable discontinuity at x equals c if f is not continuous at c, but becomes continuous at c by appropriately giving a new value to the function at c. So let me give a simple example of this. Suppose f of x equals x squared minus 1 over x minus 1. This is undefined at x equal 1. You would get 0 over 0. So it's discontinuous at x equal 1. So but x squared minus 1 is x minus 1, x plus 1. So x squared minus 1 divided by x minus 1 is x plus 1. So the graph of this function looks like this. If we define f at 1 to be equal to 2, then we have a function whose graph is this perfect straight line, and it is continuous at 2. So by appropriately redefining the value of the function at 1, we get a continuous function. So the point x equal 1 is what is called a removable discontinuity for this function. Let me look at a couple of examples from the homework. We have the function f of x is 1 over 4 minus x squared. Now this function is undefined when the denominator is 0, which is the same as x squared equals 4, or x equal plus or minus 2. So this function is not defined at minus 2 or plus 2. When x is 0, it's equal to a fourth. And when x is between minus 2 and plus 2 in absolute value, x squared is less than 4. So this is a positive number, and it's going to 0 as you approach 2. So you have a graph that looks something like this. Here. So as x approaches 2 from the left, 4 minus x squared is positive and going to 0. So the reciprocal is going to plus infinity. But when x is bigger than 2, 4 minus x squared is negative. And this is approaching, this denominator is approaching 0 from below. You're going to minus infinity. As x goes to plus infinity, this is negative and going to 0 graph looks like this. If you learn how to graph functions in your Math 155 class, you might graph this just to get a very precise drawing of the graph. So this function is continuous on the open intervals from -infinity to -2, from -2 to +2, and from 2 to +infinity. The discontinuities at plus or minus 2 are not removable. There's no way to define the function here that gives you a continuous function. The limit of this function as x approaches 2 from the right is -infinity. The limit of this function as x approaches 2 from the left is +infinity. There's no way to define this function at plus or minus 2 that makes this continuous. So these 2 points are discontinuities that are not removable. Let me do one last example from this section. This is number 47. We have the function f of x equals x over x squared minus x. Now, this is a perfectly good and continuous function whenever it makes sense, which means this is defined when the denominator is not 0. But x squared minus x factors, this is x times x minus 1. And this is equal to 0 when either x is 0 or x is 1. So this function is undefined at these 2 places. But for x different from these 2 numbers, I can write this as x times x minus 1. This is 1 over, the x's cancel, 1 over x minus 1. So what does the graph of this function look like? If this is the vertical line, x equal 1, the graph of the function looks like that. Except at 1, it's not defined, and at -1, it's also not defined. So we have 2 discontinuities, 2 points where the function is not continuous. X equal -1 and x equals 0. Now, at x equal -1, the limit of f of x as x approaches -1 from the right or the left, it exists because this is what the graph of the function looks like. When x approaches -1, this is getting close to -0.5. So if we were to define f at -1 equal to -0.5, we get rid of the discontinuity. We removed it. So x equal -1.
Question, Professor.
Oh, yeah.
Yeah, why the function is not defined at -1? It's supposed to be 1, right?
Sorry, at x equal +1. Right. Sorry. What I wrote here is correct. What I wrote here was wrong. So, thank you. So at x equal to, so this function is undefined when x is 0 or 1. So 0 and 1. But for x different from 0 and 1, for x different from 0, this function is 1 over x minus 1. So this is the point minus 1. Thank you. So we have two discontinuities at x equal 1 and x equals 0. Now, if I take the limit as x goes to 0 of this function, it's minus 1. So if I were to define f of 0 to be equal to minus 1, this removes the discontinuity. So this function is equal to 1 over x minus 1 for x different from 0 and 1. But if I define f of 0 to be minus 1, then I get this very smooth curve and the function is continuous at minus 1. So redefining the function at 0 would remove the discontinuity. But if you look at this function at x equal 1, the limit of f of x as x approaches 1 from the right is shooting up to plus infinity. The limit of f of x as x approaches 1 from the left is shooting down to minus infinity. There's no way to redefine the function at x equal 1 to make this, to get rid of the discontinuity. So the point x equal 1 is not a removable discontinuity. Yep. Okay, so that is lesson 5 on continuous functions. If you have any questions, please ask. If there are any of the homework problems on limits that you would like me to do, I'm also happy to do them right now if there's anything you want to see. Is there anything?
Professor, can you do number 79 on the homework?
79 in lesson
I think it's
2.3, I suspect.
yeah.
Okay. Okay, good. Yeah, that's a good problem for two reasons. One is it's a good problem, and second, I don't make up the final exam for calculus, but whoever does often puts a problem like that on the final. So this is number 79 in section 2.3. Find the limit as t goes to 0 of the sine of 3t over 2t. So we know that the limit as x goes to 0 of sine x over x is 1. So this is one of the fundamental facts of calculus. And the point is you have x here and x here, they're exactly the same. Here you have sine, and it doesn't matter, you could have the limit of sine of 100x over 100x as x goes to 0. That would still be 1, because what I have here is exactly the same as what I have here. But in this problem, here I have a 3t, here I have a 2t, and they're different. So this limit is not 1. And the question is, can we be clever and somehow transform this till we get something that looks like sine x over x, the same values here and here. So I say to myself, well, t goes to 0. I wish I had sine 3t over 3t, but I don't. I have 2t. But if I write this as 3 sine 3t over 2 times 3t, I haven't changed anything. That is, what I'm doing is I take the limit, I take sine 3t over 2t, which is the same as sine 3t over 2t times 3 over 3. That's just multiplying by 1. This is 3 sine 3t. 3 times 2 is 6, is 2 times 3. I can write 3 times 2 is 2 times 3. So these are exactly the same. But now I have a constant 3/2 times sine 3t over 3t. So I can say the limit as t goes to 0 for the sine of 3t over 2t is the limit as t goes to 0 of 3/2 times the sine of 3t over 3t. This is a constant. You can always take a constant outside a limit. This is 3/2 times the limit of sine 3t over 3t as t goes to 0. Now I have exactly the same thing as the argument for the sine and in the denominator. So this is 3/2 times the limit, which is 1. So the answer is 3/2.
Professor, I got the same result, but I didn't do the way that you did.
Well,
I did, yes.
so I care if you get the right answer.
Yeah, I got the right
If you
answer
do it in a
because
way
I
different
didn't
from what I do,
multiply-
it still is correct.
I didn't multiply by 3. I just take out like the 3 over 2 outside and sine t over t. Is
So
that
what you
correct?
said was you wrote 2t as 2/3 times 3t.
Yeah, no, 3 over 2 times sine t over t. Is that correct?
No. Oh, no. It's not true. So sine of 3t is not equal to 3 sine of t. That is absolutely incorrect.
Okay, got it.
I mean, so it turns out you made a mistake and somehow you got the right answer. Good.
Yeah, I still,
But
yeah.
if you
get it
make
right.
the same mistake somewhere else, it'll just be a mistake and you'll get the wrong answer to whatever you're doing.
Okay, thank you.
Yeah, no, I'm glad you asked because a lot of people make this mistake. And it's important to know that it's not correct.
Can you explain how you got the first 3 over 2?
Well, I have 3 over 2s everywhere. I'm not sure where you're pointing at.
The first
Here,
one. I mean the 3 over 3 times sine 3t over 2t.
Here?
Yeah.
Yeah, well, I have sine 3t over 2t, right? That's that.
Yeah.
See that?
Mhm.
Here I have the same thing. I didn't change it, right? In the parentheses.
Okay.
I multiplied it by 1, right? You can always multiply by 1, but 1 is also the same as 3/3. So I'm multiplying by 1, which is 3/3. Now you might say, why did I do that? I did it because I see that I interchange the 2 and the 3 and I get something that works that I can find the limit of. Now you might say, how did I think of this? Right?
Yeah.
Well, I don't know. It doesn't matter. But the thing is, I thought of it. I just showed it to you. And now you know, you don't have to invent this trick for yourself. You understand that this kind of trick or technique will work to solve a problem like this. And from now on, you can do it. So here's an example. Suppose I ask you, compute the limit of sine of 7t over 5t. Right? So work that out. What is it? So the same kind of trick or technique or method will apply.
So I just multiply by 7 over 7?
Yeah.
Okay.
And then you can interchange the 5 and the 7. So instead of 7 times 5t, that's 5 times 7t. And then I can factor out the 7/5. And this limit is 1 because I have 7t and 7t. And that's the answer. See, you can also use this trick in other instances. For example, this was a problem, not one that was assigned, I think. The limit as x goes to 0 of the sine of x squared over x. So you can't just plug in x equals 0, which you would get 0 over 0. And I have x squared here and I have x here. But of course, I would like to have sine of x squared over x squared. But if I'm going to multiply the denominator by x, I have to multiply the numerator by x, because 1 over x is x over x squared. So this is a correct statement. And so this is the limit of x times sine of x squared over x squared. And the limit of a product is the product of the limits when they both converge. So this is the limit as x goes to 0 of x times the limit as x goes to 0 of sine of x squared over x squared. As x goes to 0, x goes to 0. This limit is 0. And x sine of x squared over x squared, again, it's the same thing here and here. That limit is 1. So we get 0 times 1, which is 0, which is the answer. But it's the same idea of trying to do something to the denominator. So when you have the sine of something and you have that same something in the denominator, but then you introduce some factors that you have to deal with.
Also,
Other questions? Anything else I can do?
Yeah, 57, please.
In the same section
Yes.
on limits?
Yes.
Okay. So number 57 is the square root of x plus 5 minus 3 divided by x minus 4. And I want to take the limit as x goes to 4. So now, of course, when x is equal to 4, you get the square root of 9, which is 3 minus 3. You get 0 in the numerator and also in the denominator. And sometimes you can deal with these problems by factoring, but it's not exactly obvious what there is to factor unless you have, well, unless you're hopeful. See, I have x minus 4. Let me do something sort of strange. Let me write that as x plus 5 minus 9. Okay? Because 5 minus 9 is minus 4. And what I have in mind is what's in the numerator here. So x plus 5 is like the square root of x plus 5 squared. Because you square a square root, you get what's under the square root sign. And 9 is 3 squared. So this looks like a difference of squares, and so I know I can factor it. Square root of x plus 5 minus 3, square root of x plus 5 plus 3. Well, this is the magic trick that will work, because now this is the limit as x goes to 4 of the square root of x plus 5 minus 3 over this square root of x plus 5 minus 3, square root of x plus 5 plus 3. And these terms cancel. So just get a 1 in the numerator, and the square root of x plus 5 plus 3 in the denominator as x goes to 4. As x goes to 4, x plus 5 is 9, square root of 9 is 3, 3 plus 3 is 6. So the answer is a sixth.
Thank you.
Yeah. So this is a little sneaky or tricky, but I mean, it's basically high school algebra at a level they would never ask you in high school, at least not in the United States.
Wait, Professor,
Yeah.
you substituted x for 4 and you did 4 plus 5
Right?
plus 3 is 12, right?
No, square root.
Oh, yeah. Oh, you square rooted it first. Okay.
Well, yeah, 4 plus 5 is 9. Square
that's
root of
3.
9 is 3. 3
3
plus
plus
3 is 6.
Thank you.
Anything else I can do?
But Professor,
Yeah.
in that example, where you leave the x minus 4,
Sorry? X
What about
minus 4?
yeah,
Here's x minus 4. I
mhm.
wrote it as minus 4 is the same as 5 minus 9.
Oh yeah, I understand.
Okay.
Thank you.
Sure. So this was a little tricky part. I mean, everybody knows 5 minus 9 is minus 4, but you have to think of using that little fact at this point.
Have you graded the homework yet?
No, but when I do, you'll see it on Blackboard because the grades are recorded there.
Okay, we emailed it to you, right?
No, do not email me. If you email me, it's worthless. It's like I didn't get it. The homework is upload. You take your homework, convert it to a PDF file. You go to the assignment section of Blackboard. You go to homework 1 and you upload it to homework 1. If you email it to me, it's disappeared. It's gone. Even if I grade it by hand, there's no way I can record the grade on Blackboard. Homework is always uploaded to Blackboard, just the way the exams will be.
Is it too late to submit it on Blackboard?
It's never too late. Okay. And you can always, if you turn in some homework and decide you want to improve what you turned in, you can resubmit it. You can always do that.
Okay. Can you do number 43 from 2.3?
Yep. So in 43, you're just looking at the graph, right? And it says, determine visually what's going on and then write a simpler function. So in 43, you have a graph that looks like that. And this is the graph of a function g of x equal to x cubed minus x over x minus 1. And I want you to find the limit as x goes to 1. And the limit as x goes to minus 1. Well, you can see from the graph, as you approach 1, the limit is 3. As you approach minus 1, the limit is 0. So this is determining the limit visually if it exists, and they both exist. And write a simpler function. Well, if you take x cubed minus x, you can factor that out in x, and you get that. And x minus 1 factors like that. So if you divide by x minus 1, these x minus 1s cancel. And this is equal to x. Oops, this was 2. Looking at the graph. You get x times x plus 1.
Obviously, I got confused.
And then it's clear because the limit as x goes to 0 of x times x plus 1 is 0. And the limit as x goes to 1 of x times x plus 1 is 2. So that's what they wanted you to do.
Thank you.
Get the limits visually and then get them by simplifying the function.
Okay, thank you.
Sure. Anything else? Happy to
Hi,
oblige.
Professor.
Yeah.
I was wondering if you got my email yesterday about my current situation and the private message that I sent.
Just a second. Oh, so there's no penalty for turning homework in late. So if for whatever reason you can't turn the homework in on time, I still want you to do it and turn it in. You don't lose any points. I just always encourage you, if whenever possible, to do the work on time, because otherwise you're just falling behind and you have a lot to catch up on and a lot to learn. But if you turn the homework in late, you'll get full credit. There's no problem for you with that.
Okay, thank you.
Sure. Okay. Anything else?
Yes, Professor.
Yeah.
Lesson 3 to 4, you said to do the appendix A, theorem 2.8, right? You said to read that and do 2.2 exercise 39.
Right.
Yeah, so
You want me to do that?
I couldn't find it. Right.
Let me see. So here I have in my book an appendix A, and appendix A theorem 2.8. So Theorem 2.8 in the appendix, the theorem was stated in the text and I talked about it. And what's given in Theorem 2.8 is the proof of the theorem, which is the squeeze theorem. And where it refers to 2.2, number 39. So let me go to chapter 2, section 2. And
So is the on chapter 2, section 2?
I assume so. So in chapter 2, section 2.2, number 39, I'm not sure why they're referring this to the squeeze theorem, but let me look at something else. Yeah, I think with respect, so section 2.2, number 39 is a very interesting problem. It's not part of the homework, but it's certainly, if you're interested in mathematics and the theory of mathematics, this is a good problem to think about. And in section 2.3, they also suggest numbers 118 and 125. And yeah. For example, 125 says if you have two functions which are equal.
Professor, can you give me the page number, please?
Well, in my book,
Yes,
it's page 89.
page 89. Okay, thank you.
Yeah, yeah. But I mean, these are problems that really depend on having a very good understanding of the technical definition of a limit. Yeah. Okay. All right. So that is it for today. And study hard. Supposed to get pretty cold, I believe. Stay warm. And we'll be back on Monday. I will set up an office hour probably sometime on Friday. If you want to log on and have any other particular questions you would like me to do or to answer. Okay. All right. Be well, everyone.
Thank you,
Bye-bye.
Professor.
See you, Professor. Thank you.
Have a nice day, Professor.
Bye.